This is not AOC. No, um, it's continuing AOC in spirit. So now that AOC is done, we are continuing with the Synacor challenge. So this was also created by Eric Wastl, and if you're familiar with the Intcode problems from 2019, it's much like that. Oh, you did 2015 day 19. Cool. Did you end up using like a recursive descent parser approach? I still want to go back to that, but I think that's probably what I would want to do. Now that I know that it has that kind of structure. Wait, you use memoization? Really? You just ran the... Oh, okay. Well, fair. Well, I'm glad that worked. Letter plus left index and right index. Okay. Yeah, I'm surprised. I'm gonna have to think on that. I think I still want to go back through it with like a parsing approach, as if I were parsing the JSON. So like backtracking and alternatives. But yeah, yes, we get a day 13. Synacor for now. And then I'm thinking maybe advent of FPGA. And perhaps I'll finish 2015 as well. Maybe, if I get stuck on Synacor, that can be my cooldown. Need to believe your day 19 suffering was worth something. Fair. Yeah, I want to revisit that. It's not December 2026. Not yet. But I might do the same thing next year where I solve 2016 alongside 2026. And then that would leave me all of these events are just free game for me to do throughout the year. I haven't finished 2019, but the problems I've done are all int code problems. So we could probably look back at what I did there because it'll probably be similar to what we're doing for Synacor. It seems like day 15 was the most advanced one that I solved, but they all use the same machine code. So, the Synacor challenge, that's a link to something. Oh, there's an archive page for the Synacor challenge. Cool. Well, let's have a look at that. Please don't scroll back this. Donate. Um, okay. This is a programming challenge, but you can use any language you like. So we'll use Scala. I'm going to put this all in the same Advent of Code repo. So I'll have access to the same tools. As you complete sections, come back here to check your answer codes. All right. I guess we won't really have a way to check our answer codes, will we? But I can ask around about that. Probably Zuno. I just I can check my answer codes with you. Okay. I assume you've finished this, given that you're mirroring one of them. So did you do this like as it came out? So as you progress through a challenge, you will encounter 8 unique codes. Below are there... Oh, wait, these are the hashes, so I can verify them this way. Okay. I can verify the hashes that way. You did this a few years ago while the website was still up. Cool. Yeah. Your solution for absolutely. Let's do some of that before jumping into the challenge. In the meantime, I've set up my repo. I've got the binary in here. So we'll just pull that out. So that binary equals, there's the link. Okay. Let me click on that. A day 9 spoiler. So day 9 was the boundaries problem, right? Is this a standard ML? Yeah, standard ML. Cool. So you have a structure, and then so this is for a point. You parse the input. We build all the pairs. Let me just pull up the problem description so that everyone knows what we're talking about. All right, for this problem. So you found the circular windows. Okay, so this is for the pairs of that build the borders, right? And solve threads. You pair the reds, create the red points. You get the area of the, so this is for part 1. You just get the area and then max 1. Map area there. Okay, cool. And then all the intersects. So given x, y for 2 different points, and then previous x, previous y. So this is a recursive function, right? And it's going over the previous instance. And basically, you just check those points to find the intersections. Okay, and then how do you use it? So we solve for this part. We get the rectangular pairs, and then list.filter, okay, lines, okay. We take the lines, we look for the intersects. Okay, great. So it's the same kind of approach as mine. Find the intersects. Cool. That's clean. It's nice to see ML. I don't read ML very often, and I've never played with it. Cool. Thanks for sharing that. All right. So to the Synacor challenge. We can pull out the binary once it's necessary. Okay. In this challenge, it's your job to use this architecture spec to create a virtual machine capable of running the included binary. So that's the first step. We will find codes, submit these to unlock. Okay. So the architecture. There are 3 storage regions. So there is a memory with a 15-bit address storing 16-bit values, 8 registers, and an unbounded stack which holds individual 16-bit values. Okay, so memory register stack. All numbers are unsigned integers. Okay, 15-bit. And all math is modulo, is that 2 to the 15th then? No, that's 2 to the 16th. 2 to the 16th. No, that is 15th. Right. So the max value of the 15-bit unsigned integers. Okay. So we could just use shorts. Maybe. So the binary format. Each number is stored as a 16-bit little endian pair, low byte and high byte. Okay. We have a pair of bytes. We have some literal values. And then some particular values are reserved for registers, and then the rest are invalid. So I guess these are the last 8 values of the 15-bit range. You have to implement a VM. And then programs are loaded into memory starting at address 1. So that's where we'll put our program counter. And address 0 is the first 16-bit value, address 1 is the second 16-bit value, etc. Okay. So after an operation is executed, the next instruction to be read is immediately after the last argument of the current operation. Wait, last argument of the current operation? Oh, that's weird. Is that, am I reading that right? Oh, I wish this had word wrap. There's gotta be a word wrap. I guess we could just look at the raw. And that will wrap. Cool. Okay. The next instruction to read is immediately after the last argument of the current operation. If a jump is performed, the next operation is instead the exact destination of the jump. Okay, so this is weird. So the program counter doesn't just increment. Right? I'm not wrong for thinking that's unusual or misunderstanding that. Encountering a register as an operation argument should be taken as reading from the register or setting into the register as appropriate. Okay, so some of the values are reserved as registers. I think in our VM, we'll probably explicitly, or in our emulator, we'll explicitly number the registers anyway, and then we'll do a translation from a number into either a constant or a register address. Hint, start with operations 0, 19, and 21. This program occupies 6 memory addresses and should store. Oh, okay, so we can use this to test our emulator. Okay. So we have a listing of opcodes. So for today, probably we'll get as far as modeling this. So modeling all our opcodes and at least getting the structure of our emulator. I am still tired after admin code. So we'll keep it not too long and just set the framework, and we'll do the real problem solving come Monday. Okay. These are the opcodes. I think I will just read the definitions of those as I'm adding them in. Push A onto the stack, etc. Okay. I think for reference, so we'll start this in a worksheet, and as necessary, we'll put it into an actual source file. But I like to start with a worksheet so that we can explore things a bit. And for reference, let's look at 2019 code. So here's my implementation of the Intcode machine used for this problem. And what I did here, I had my opcodes enumerated. Every problem added new things. So by this time there is a mode. And this state is my VM emulator, right? So there's memory. There is a program counter. And at any state in memory, you can execute something. So I have a bunch of helpers here. So this lets me grab a parameter at some position. This lets me parse a value, etc. But the most important thing here We can go over these helpers later. We'll probably do something similar to these helpers. The most important thing here is the step. So we have some input. I'm not sure what the, oh yeah, this was like the input to the program, which we might not have in the same way here for Synacor. But in this case, if we look at add, so this writes a value. Why is opcode a parameter there? Well, I guess we're progressing based on opcode, and what we write depends on the opcode. Yeah, so progress happens in all of these, and progress, I think, will it moves our program counter. So in this case, it's +1. In the case of Synacor, it will be that we're jumping around. Right here updates the memory. So we make a copy of our current state with the memory updated. So when we add, we make a copy of our current state with the memory updated, and then we also, again, make a copy of our state with the program counter added. And the reason I did it this way was so that I can go forward and backward in state to search around. So all the state is immutable, and we can jump to a particular state for debugging and whatnot. Oh my. Jorschenheimer. Am I reading that? Thank you for the raid. So we're doing Synacor here as an extension of Advent of Code. I assume maybe you were doing Advent of Code? Hello, hello. So if you're doing Advent of Code, you might recognize this. Advent of Code is finished. So we finished day 12 yesterday and did a retro and everything. And we're continuing that with Synacor. So if you're familiar with Advent of Code 2019, there were a series of Intcode problems. So there was like an Intcode virtual machine, and you had to design an interpreter for it. And then all the puzzles for that year were inside this Intcode. You had to run the interpreter and run like run programs and kind of reverse engineer them and whatever. So that is much like Synacor, which is a challenge written by Eric Wastl before he wrote Advent of Code, where you're basically given a large binary file and you're given these the specifications for a VM. So here's the architecture. And the first step is to implement this VM and run that binary. You were doing some reverse engineering stuff. Okay, cool. Well, I'm pretty sure this will involve reverse engineering. So I don't know too much about what's going to happen, but I do know that this is an 8-part puzzle. So inside of this binary are hidden other puzzles. So we'll have to reverse engineer it, figure out what's going on, and find the puzzle before we even get to solve it, right? So a little daunting, but we're taking it easy. Today's just going to be kind of the setup day. We're going to start modeling our VM. And then maybe on Monday, we'll find our first puzzle. Yeah. And apparently Eric made this as a recruitment tool for OSCON. So he did this for a company that no longer exists. They went to OSCON and had this as a challenge. You solve this and then they try to hire you or something like that, which that's a big undertaking for recruitment. But it looks fun. It looks fun. It looks challenging. So backseating is very much encouraged here. I mean, unless there's, and you already have all the answers, don't just tell me the answers, but probably I'll make mistakes. I know, right? Okay. So I was just going over my code from 2019 for the Intcode, and I'll probably base my VM on this design here, where I have a state that has its memory and its counter, and it's immutable. So everything I do um, makes a new copy of the state, right? So if I jump to a different address, we make a copy of our state with the instruction pointer updated. And actually, our steps. So when we run a step here, this is important. We create a new state, yes, but that step also has an output. So some opcodes we do have some outputs. I don't. Let's see. Out. I guess just out. So you can output values along the way. And this actually kind of makes it. If you squint, this is basically a state monad. So I could implement this in terms of a state monad and then just use the for comprehension syntax from Scala to work with this. But that's not something I think I did back in when I was working on a 2019 problem. But yeah, like the cool thing about these problems was that so I'm still doing like my normal admin code stuff, right? Here's the point class and directions and whatnot. But then I you have to run this program in order to in order to actually solve things. So like it's a mix between like the high level, normal level points and whatnot, mixing with the VM. And I imagine we'll have a lot of that kind of stuff too for Synacor. Okay, so with that, um, yeah, let's do some modeling. First, we'll do opcodes, and maybe I'll just add this in line as a description. Mm, we'll see. We'll enumerate them, and then why don't we just start with our step function, and then we match on those, and then we can read these instructions off, or we can read these descriptions off as we're implementing that, and we'll see what else we need as we're doing that. Um, so something like this. We have halt, set, push, pop. I'm going to put these all on separate lines. I guess if it's a separate line, it has to extend opcode. Okay. Push, pop, equal, greater than, jump, JT. I'm not sure. That's some kind of jump. It's a conditional jump. Okay. JT, JF. I want something more descriptive for those. We have add, molt, mod, and and we have or not. Okay. I kind of want to group these. So we have here's math functions, here moving, here's equality, and then here's, I guess, really low level functions with registers. And or not. Read mem. Whoops, what's going on there? Read mem. Write mem. Call. Write the address of the next instruction to the stack and jump to A. So I guess that's like calling a procedure. So we jump to that function. And then, oh, these numbers are the values of the opcodes. All right. And I do take advantage of, so when you make an enum in Scala, these automatically have like an index value. So I do have to make sure they're in the same order so that halt remains 0. So call, we have return. Move the top element from the stack and jump to it. Okay, so like after jumping, then we have out for output and in to read characters. So I'm going to ignore out and in for now and focus more on these. And let's see how we did this. I think there are enough of those. I'm not going to do anything special with these. I'm going to put them all in one line. So let's just multi-line comma these all out. No, I have a key binding for this. There we go. Okay. And what is the issue here? Am I doing something wrong with the syntax? Nope, it should just be that. Do any of the opcodes skip values? Good question. What do you mean by skip values? I mean, there are opcodes that jump to some address. And then return jumps back, out and in, read and write. The values of the instructions? No, I think these are in order. Yeah, yeah. Good, there's no reserved values. I think in Intcode there were some reserved values for a while. Okay, and then number of params. Yeah, let's do something similar to this. Because I'm sure that will be important. So let's look at our play worksheet. So which ones have just one parameter or 0 parameters? So halt. You know what? Let's go. We could do this. We could do this backwards. Let's start from the ones that have A, B, C. There we go. If we highlight it, we can find them quickly. All right. So we have equal or greater than or add or mult. And why do these have 3 values? Set A to 1 if B is equal. Okay, so A is like the output register. And then B and C are the actual like arguments. So mult, mod, and or. Okay, and in this case, we have 3 parameters. Now we're just looking for 2 parameters. Oh, this is a little bit annoying. You know what? If I do this in the terminal, well, I can't regex that either. Whatever. We'll just go through them one by one. So we have set register A to the value of B. Makes sense. We have jump to and jump from, or no, jump true and jump false. I see. Jump true and jump false. Makes sense. Then we have not. We have read mem and write mem. And yeah. So these will all have 2 parameters. And now let's look around for all of the A's. Oh, we can't really highlight that. But highlighting the A and B will help us avoid certain lines. Maybe that works. So push. So case, push, and pop. So those are our stack operations. And we have jump. We have call, out, and in. Call, out, and in. So these all have 1. And then anything else we can assume just has 0. All right. And we still have some weird syntax error. Oh, wait, case. Case. There we go. And equal is not found. Do we miss it here? You know, we need to break these up into multiple lines. Yeah, equal is before greater than. Equal and greater than. Okay. Yeah, let's break this up into lines. Can we do it that way? Okay, I think so. Great. So let's put our jump instructions here. And then let's do our math instructions here. Our Boolean instructions here. Case. Our memory instructions here. Call and return. Let me try to understand call and return. So write the address of the next instruction to the stack and jump. Okay, so these are, you call a function and you're going, these are like function stack opcodes. And then our writes, our output, input opcodes. Cool. Equal than, greater than. I'm going to make these their own line too. So they are our tests. Okay, there we go. There's some organization. Now, I mean, the way I do have maybe a slight concern that this won't be optimized enough because, you know, we're doing a trade-off here where we focus on making like the modeling really nice. But we'll see. We'll see. If we need to optimize later on, we can do that. Great. So now we have our state, case class state. So there is it has a register bank. I might just put registers in a case class with all of them named. There are 8 registers. We can just call them A through F or A through G, H, or we could just have like an array of length 8. I'm going to make a whole case class with registers in case I want to set the values of registers for some sort of testing. What exactly is in a register though? So register. So there's registers 0 through 7. I'll call 0 through 7 A through H. Encountering a register as an operation argument should be taken as reading from the register. So registers just hold 16-bit values. Now, Each number is stored as a 16-bit little endian pair, so a pair of bytes. I was thinking of just doing a short, but maybe we'll want like low byte, high byte. We could make a number class, I guess. I'm not sure. So there's a low byte and a high byte. And little endian means that the left side is let me just double check that. Little endian. Um all right, so each group is assigned a number. Wait, just which is the end? So big endian. Big endian is what we normally have, right? Or is little endian what we know? Okay, let's do this. Google, is a JVM little endian? Little endian, the value 1, 2, 3, 4 is stored at 34 and then 1, 2. Okay. So the endianness here is different from what we're used to. So low byte and then high byte. Okay. Right. So in little endian, the value of 0x1234 would be stored as 3, 4, and 1, 2. Okay. Oh, 3, 4, 1, 2. It's not even 4, 3, 2, 1. Yeah. I haven't even thought about little endian. I know, like there's a mention of it in your like architecture class or whatever, but then you do everything with big endian. So you work with a little endian system. So I'm curious if you know, why would you ever use a little endian? What's the advantage there? Okay, so low byte and then high byte. I think we will model it this way. We can optimize that later if needed. And I guess if we want to do math, we want to interpret this as a short. So def as short. Well, our shorts are signed. Yeah, they are signed. But the bits should still be the same, right? So we can just do high and we shift high to the left. How many bits? 8 plus low. And then that should be as a short. Correct me if I'm wrong there. That's not something I want to think too hard about. Found int required short. Wait, high is a... Wait, once you shift it... Oh, once you shift a byte, it becomes... can you make a short from bytes? I suppose we could just do that too short plus low. That'll work out. We can optimize that later. Found int. And we required a short. How did we get an int? I guess when you add a byte, you get int. So I guess after the add, we also have to convert to short. So why don't we just do the whole thing? Let's just do the whole thing as an int, and then we can convert to short. Or we can do masking. I'm not sure. We'll have to add in some tests for overflows to make sure things are working properly. To do test overflows. Okay, so then a register is just storage for 8 numbers, right? For the number, I'd probably just use a uint and the value with a mask when assigning. Yeah, that makes sense, but we don't have. I don't think there's a uint in Scala by default. I could just use assigned int and mask it. Well, high is a byte, so when I do shift it left, then it turns into an int. So this is 32-bit. And then once I add this low, that'll also be in 32-bit. And I just converted it all too short. But we can test that later. Yeah, just shift all 8 bits of the byte and add. So we have registers, so this will go into our state. Yeah, that's fair. It's pretty. It's meant for the JVM, or like primarily runs on a JVM, so it's just going to use the same types there. I mean, I could check. Does a JVM have a uint? I don't think it does. No native support for unsigned integer primitives. Except car. Okay, I guess car is 16 bits and it's technically unsigned. But I don't think we have to think about that yet. So we'll run into it when we run into it. And that gives me time between streams to like think about how I'll represent this more accurately. What's important for now is that this works here. So val a, or no. So we have a, that's num, b num, c num, d num. Like, I don't know. I might just later decide that I'm gonna implement num as a character. And then I could just do masking magic when I do my math or something. But either way, it's nice to have a separate type for num, and then we can define what it means to add on nums. And then, the masking or whatnot is just implementation detail. And we can inline those defs so we can make them efficient if we need to. So E, F, G, and H. And I'm also going to give it an apply method. No, we'll leave that in there. So def apply so that we can index into it. So there's an index, and this will return a num. And how will I do this? I could just match on the index. So case 0 goes to, right? Like that, that'll work. And we gotta fix the numbers. Or we could just put all of the values. We could put all the values into a vector. And then when we apply, we just get that vector. Values equals, we can make that an array. Array A, B, C, D, E, F, G, H. So this apply will just get those by the index. And then it throws an exception if it's not 0 through 8. Okay. So there's that. We have registers. And then we're going to have a stack, but we can skip on, we're going to have a stack in memory. We'll just put placeholders here. So type stack, let's make it a list of num. And type memory is just going to be map from num to num. And then if you want to change the implementation, we can just change that into like a class definition or something. But for now, it's a type alias. Oh, great. Yeah, I'm glad that that's helpful. I expect that most of my audience isn't familiar with Scala. So I appreciate that people come in here without knowing Scala, because otherwise there'd be like two of you. Um, yeah, the Scala folks don't really show up. Today is the last true day. No, it is not. I'll be back after the weekend. I'm gonna take weekend breaks now. Great. So let's start implementing some of these. We'll have a step function. And let's look back at our 2019. So So 2019, we had a step function. There's some input, I guess. Opcode. So the opcode will just get, yeah, from our current instruction. For now, I'm just gonna make opcode a parameter of the step function, and we can refactor that later. So we're gonna match on that. Oh. A step is just gonna give us, for now, it's just gonna give us a new state. But maybe there'll be an output. So op.match exhaustive. And I am gonna default all of these to this. So by default, they do nothing until we write a definition. That way it stays compiling. And now let us look at some definitions. Let's go with straightforward stuff. So add. This assign into A the sum of B and C. So we have to get the three parameters. And I suppose A can be one of two different things. It can be assigned into A. Well, I think it's going to be a register. And I suppose B and C are simply values, or are they? I'm not sure. Let's make sure we know what those actually are. Execution. Encountering a register as an operation argument should be taken as reading from the register or setting into the register as appropriate. Okay, so we do have to have a way to parse our arguments and then determine if it's a register or not. Yeah. And all numbers are all math. Where's the interpretation? these numbers instead means registers 0 through 7. I might make those an opaque type that just defaults to num. An opaque type for a num. And if we see those, we interpret that as a register. Okay, these mean literal value. So programs are loaded into memory starting at address 0, the first 16-bit value. Okay. Oh, it says start with 0, 19, and 21. Great. So halt. I think for halt then, well, let's make this optional. And then in this case, we can just return none, right? So there's no next state when we have the halt opcode, which means all of these are going to be sum. Yeesh, I might want to refactor that, so I'm not doing that everywhere. But in this case, there's none. Halt and catch fire. we could print line, throw an exception with fire. Okay, and then 19 and 21. What are 19 and 21? Out and oh, there is a 21. No operation. Okay, let's add that. Case no op. Does no op really mean no operation? Well, the state still advances, right? Because after an operation is executed, the next instruction is to read is immediately after the last argument of the current operation. But if no op has no arguments, oh yeah, immediately after the last argument of the current operation. Oh, hold on. This is normal. Okay, so this is a stack-based VM then. So then what I'm imagining, is, let me get my whiteboard. So we have 3 numbers, and maybe we have like the add opcode. Oh, my thing is messed up here. So we have add and then x, y, and then the next operations here. I'll have to fix my whiteboard coordinates in a sec. So a no-op can precede that, right? We can have a no-op here, and it just moves down to add. So we still do need like a program counter. So PC, and that's gonna be a num. I'm really wondering if I should just alias num to int. It might make my life easier for now, right? Like an alternative implementation is just type num equals int. But we'll see. Okay, so even in the case of no op, then case opcode.no op, then it's not just sum this, it's sum this.copy pc.increment. And we'll have to implement that for a num. So let's define some methods here. So def increment, and it gives us another num. And I suppose we increment the low byte. So little endian is the ordering of the bytes. It's not the ordering of the bits. So the individual bytes are still in like the order we're used to. I hope I'm understanding that right. So we'll do copy and low equals low plus 1. But when you add on a byte, right, so we have to turn that back into a byte. That's a little bit annoying. I feel like low should have, or a byte should have like a plus method, right? Like you can do plus byte right here. Oh, wait, one has to be a byte. 1.2 byte. Sure. There should be a way to write that. Let me just pull up like a Scala console. So in Scala, there are a few ways to write numbers. Oh, that seems dead. Just pull up a new console. Or, I mean, we have a worksheet. We have a live worksheet. We can do that here. So let's comment out this for right now. PC equals PC, but we're going to change that. So the numbers that we can work with, we can say 0x FF, right? That gives us a number in hexadecimal, and I think we'll interpret it as an int, about x. Yeah, that's an int 255. We could also do 0b 100. That should be a 4. This might come in handy. Well, I mean, both of these might come in handy. So that's good to have in our back pocket. But as far as making a byte value, so like for a long, we would do 1, 2, 3, 4 L to make it a long. But 1, 2, 3, 4, I don't know, like B, no? Let's just look up byte literals in Scala. Byte literal Scala. There's no dedicated syntax for a byte literal. So you define an int literal and use a 2-byte method or leverage implicit conversion. And for whatever reason, implicit conversion isn't really helping us here. So we'll just do an explicit toInt. Sorry for that little diversion. So nums, we have to be able to increment these. Low plus 1.2 byte. Okay. No, not okay. Found int required byte. Oh, the plus method, even if the parameter is a byte, it's still going to return an int. Fine, so we do low plus 1, not 2 byte. Um, to do overflow, we can handle that later. I want to get over like the general framework before we get into that. We can do an infix def of plus. So this is new in Scala 3. In Scala 2, you could just define symbol names. Or like any name could be used like in infix form. And then there's like rampant abuse of the syntax of Scala. So now they prefer that you declare that a method is actually an infix. So n is another num. And you know what I could do is like conversions between nums and ints, do the math in int, and then convert it back into a num. But for now, we'll do something dumb. Well, we won't be running it quite yet. So eventually we'll add in some tests. We just want to get this out of the way. We just want the type definitions. Um, so we're going to copy n.low plus low, and then n.high plus high, and then to do carry. We can do that later. Or I guess this is just a new num altogether. Don't need to copy. Okay, so this is a copy PC, and PC is incremented. Okay, so that's 21. 19, out. Write the character represented by ASCII code A to the terminal. Okay, so we need to convert our num to a character. So def as car. We'll just do high followed by low. So it's basically sort of as short dot to character. Okay, that should do us. There's something we don't like here. Okay, we have to convert back to bytes. I'm surprised this isn't handled by implicit conversions. So not something I'll debug on stream. I can think about that offline. And then, explain the fix later. Okay, so we have a plus. Let's try add. Actually, pc.increment. Is it going to happen? Okay, it's going to happen the same way for most of these. I think for 2019, what I did was have a special function for incrementing just one step, but that's like a cleanup we can do later. I think I'd progress. Yeah, so IP becomes IP plus 1 plus the number of params. Oh, okay. Yes, that's important. Yeah, let's make that its own thing. So we have a helper method here, def progress, and that gives us a new state. And it will depend on the opcode. So op is an opcode. And for now, we won't do num. Well, actually, we do have num params. So op.num params. Great. And we have what do? We copy our current state, but we increment the program counter. PC equals PC plus 1 as a num plus num params. Now, I think what I want to do to make my life easier is do a plus method for ints. So if we're given an int, then we can create a num. So we can just take our n and we mask for the low bits. So n and 0xFF. Is that a full byte? Yeah, that's a full byte. Plus low dot 2 byte. And then we do something similar for our high bits. So n, and we mask that with 0xFF00, and then convert that to byte. Okay, so now we can just add our normal Scala integers to a num. And probably this conversion, we could maybe make that an implicit conversion to do implicit conversions. Think about that. Great. So now we have progress given our op moves the program counter. So our opcode here is just going to be this dot progress with the opcode, and that's all it does is just progress. And in this case, that's going to be 0, right? Great. Now, what else do we have? Let's go back to the instructions here. Oh, we wanted an output. Start with the operations 0, 19, and 21. So 19 gives us output. So this is going to return an option of state and output, which is going to be a character. And out in particular, right, the character represented by its argument. Okay. So we still have to have a way to get the arguments. Memory. I had made memory a map from num to num. Memory could very well just be a vector or an array of nums. There's a chance maybe I do that as an array of shorts, but the point is that whether it's a map or a vector, like we can index into it by a num. Or, an int. And why are we talking about that? Because we're about to write out, and we need output. Oh, hold on. The output of a step is also optional, so most of them are going to have no output. So this is an option of state where the output itself is also optional here. Okay. And let's look at how I'd modeled this previously, because I think I had a nice helper function for that in 2019. So let's look at no out. Right. So if you have no output, we just kind of wrap everything up. So def no output is going to be sum of no output to this. And that is a method on a state. Great, so now we can remove all these sums. That'll clean things up a little bit. So we can just do this dot no output. Okay. We don't even technically need this. Like we can just do dot no output. But I'm going to leave this in there for now to keep things explicit, so that we know we're operating on our current state. Great. And in this case, we're going to do this dot progress. And then after progressing, we say no output to wrap it up nicely for our function. All right. And then now we have to be able to parse our arguments. So I could just call them A, B, and C. Let's think about different ways to do this. So we can do def A, def B, def C, where these all just return nums. And the reason I hesitate with that is like, what if the num actually represents a register or something? So there needs to be like another step where we actually interpret what that num means and not just as a constant. Rampant syntax abuse in my cover band. Yeah, a Scala cover band for sure. That's part of the goal of Scala 3 is like Scala 2 is like very general, and with 3 they're like, okay, so there are these like hacks that we figured out we could do. Like turns out the Scala 2's type system is like the type system itself is Turing complete. So you can do like arbitrary computations within just a type system. So they formalize things, and things like implicits, like you use implicits for everything. So if you know what an implicit is, it's just like a parameter that's automatically passed along, right? But it's more than that because implicits can be used for like a derivation. So basically, you might not know what you want to build yet, but if you can infer the type, then you can also like construct an implicit on the fly. So you can like construct the thing that you're building just because of type inference, right? So there's like use for derivation, for type classes, et cetera, and those things are more formalized in Scala 3. Um, but yeah, no one would have predicted that the implicit system would be so powerful. I do use Scala for my job. I've used it for my job for the last decade plus at this point. Um, yeah, so I'm thinking about doing this. We still have to decide whether it's a register or a constant address. I'm not sure. Um, now, what do we do here? So here, we would just get the values. What is value? Okay, value at a position. Um, so we would index into the arguments. Um, that's not a bad way to do it, but how we'd interpret the argument depended on the parameter mode. Interesting. Okay, so if it was, I don't remember what pos, im, and rel mean. Relative memory address. Pos is a position. And im is a param. So memory IP plus 1 plus position. Okay, so im is gonna be kind of our default interpretation, which is as a parameter. So we'll look into the memory at our instruction counter plus 1. What kind of programs do I work on my job? So usually it's some sort of distributed system. I've done a lot of APIs, data pipelines, like streaming stuff. I don't know. Yeah, often for like a financial institution or a streaming service. I worked for a few streaming services. I do a lot of consulting and contracting, so I've seen a variety of companies, and yeah, it's mostly been like some system of microservices of some sort. Um, Great. So what I want then is this param method. We could do them. We could do them directly. We could reference them by position. I think I like the idea of doing it directly. Wait, no. M means memory. So we go into memory And we look at, oh yes, right. Memory is just going to be the thing in front of us in the program. So the parameters, we'll just define them this way. That will be a nice kind of shorthand. So A, that's going to be a num. And I'm going to leave this comment here because there's still something to think about. So we're going to look at our memory and we're going to get PC. So PC is a num dot increment. Okay. So this is going to be memory PC plus 2. Let's just do PC plus 1. PC plus 1, PC plus 2, and PC plus 3. Yeah. And then there will be certain memory locations are just the registers. And I want to encode that in the type system in some way so that we're not accidentally referencing, registers when we're not supposed to. But to do memory register safety, something to think about offline and bring here to the stream. Okay, so now something like add. Do we have what we need to implement that? Sponsored by Twitch? No. I don't think Twitch uses Scala. In fact, I think Amazon as a whole doesn't use much Scala. They use like Spark jobs. And they don't hire contractors. I've talked to like some Amazon Scala people. Yeah, I really want to do add. Okay, so store into A the product of B and C. So A we're going to interpret as a memory location then. So we're going to do this dot copy. No, we're going to write a store function. So def store, and there's going to be a location. We'll call it position. Store positions in num. And this is just going to give us our state. This dot copy the memory updated. Memory equals memory dot updated. And at that position, we're going to write the value. So this will take 2 parameters, v value. Okay. So now when we do our add, we can do this dot store at A B plus C, right? And then no output. But no output will progress our counter. Cool. Twitter used Scala back in the day. Yeah, Twitter was a huge was like a huge early adopter of Scala. I think they started using it like in 2009 or 8. They moved from Ruby on Rails to Scala. Which big firms use Scala? Well, let me think. There are a lot of them. Like we could think by category. So streaming services, Spotify has a big Scala team. Netflix, Disney streaming is all in Scala. Netflix uses some Scala. They have a lot of Java too. I don't know where they draw the line there. SiriusXM, Pandora use Scala. There are some banks. So there are, let's see, Capital One, Credit Karma, Morgan Stanley. There are like a few hedge funds that use Scala. Gemini uses Scala, the cryptocurrency exchange. Tubi TV uses Scala. I think LinkedIn had Scala. Starbucks, yeah. And I don't know. Those are the big names I can think of right off the bat. Yeah, it seems popular in streaming services for some reason. Okay. Mhm. Yeah, and they all struggle to find Scala developers. So if you learn Scala, you can get good money from them. So we were able to implement, oh no, value is just another num. Great. Okay, so when we store, we update the state with a memory update at that position. Cool. Then we could do the same for molt, negate, etc. And as long as we have a type num with a plus on it, it doesn't matter what our underlying implementation of num is. So we can always change that later. So booleans, how do booleans work? Let's look at and. Store into A the bitwise and of B and C. Okay. Why don't we go to our num type and implement these various operators. So in fix def and what do you recommend as a beginner Scala project? Advent of code. Yeah, pretty much like the same kind of beginner projects you might do with a Java project or whatnot. So anything you want, but starting with Advent of code is nice. If you're looking for where to start, Lee Hao Yi wrote a book, Hands-on Scala. So it's available online. He also wrote Hands-on Scala JS, which honestly, that might be the place to start. If you're already familiar with JS, so you could just use like all your JS stuff, but like from within Scala. So this is Scala compiled to JS, and you get the visuals and whatnot. Oh wait, there's a book by ___.io. They have some books. So training, consulting. Where are the books? Essential Scala. This is a place to start. There was also like a visual Scala. There's a creative Scala book. This one's fun. So this teaches functional programming via like a graphics library called Doodle. So like it emphasizes functional programming, but it's like with doing it in a creative way. So this is really cool. So like maybe that. Just start with a book. When I started Scala, I basically just read the big white book on Scala and just started using it for. I think the first thing I did with it was Project Euler, and then I learned Play Framework and started like building uh, some web apps, just like toy web apps, that kind of thing. Oh yeah, I can link those in chat. So I'll link Creative Scala, and there are others. Um, yeah, the others are there in the link too. So they have like Advanced Scala for functional programming, Advanced Scala with shapeless. So this is a little bit outdated now, but this This is for like type level programming. So remember when I said the Scala type system is Turing complete? Um, Shapeless was the way you did all this stuff back in Scala 2. And now like Scala 3 has formalized some of this, so I'm not sure this is still um, necessary, but it's still cool. All the type magic you can do. Okay, so an and for nums. Um, Basically you're gonna make a num by anding the low and the high. So n and low, or n dot low and low, and n dot high and high. And what else will we need? We have and, or, we have not. Oh, what's wrong with this? Oh, right, we were going to do or, bitwise or. Um, and then not. So def not. So this is a prefix. Oh wow, it's been a while since I've written like a prefix method. I'm not sure how to do that. We'll ignore that for now, or we can just do not. We'll comment that out. Get it when we need it. All right, I've got to use the bathroom, so we're gonna have a little break. I'll leave this on screen. Hmm. The Red Book. That was great. I highly recommend. There might be better stuff by now. Like multiple people have written like functional programming for Scala books, but it's still a classic. Um, yeah, totally. Drop that link in chat. It's a good one. Alrighty, I'm back. Yes, that is the White Book by Artema. So that's kind of like the official Scala book, and I think it's actually pretty well written. And it has like fun examples to work with throughout. So I like that, and the fifth edition, it's all updated for Scala 3. There's a lot of material that's still not updated. Like I don't know if the Red Book is updated because you would do things a little bit differently. But the nice thing about the Red Book is that it's almost language agnostic in that like the focus is on teaching functional programming principles. And then it shows how you do this stuff in Scala. And in particular, it's like the type functional programming, so it teaches about monads and whatnot. That's my favorite still, the White Book. I suppose so. Like it's still like a good reference. But I wouldn't say it was like mind blowing or anything. But it is a good book. Okay, both of these definitions require a conversion back to byte. Yeah, yeah, it's old now. But the functional programming libraries in Scala, this would basically teach you how you could implement those. So like cats and Scala Z back in the day. So like the definitions of monad and functor and all that stuff. All right, and or not. Let's think about that later. Let's get mult there. And I think instead of providing an option for like multiply by int, we'll just do some conversion. But I don't think that will come up. Not yet. Oh boy, multiply. I guess I could convert these to short, multiply there. I mean, like, because this will definitely overflow pretty quickly. So if we're going to multiply, we can do num dot from short. And what we could do is as short times n dot as short. And I do wonder, like, I think it works as a hack. I'll have to verify this later. Even though shorts are unsigned, we could just multiply them, or they're signed. We can multiply them even though they're signed, and the bits still work out the same. It's just an interpretation. So if we convert that back and forth, to do verify unsigned or signed works. Okay. So we need to implement like a num dot from short. You wonder if SICP could get a Scala treatment. Maybe, but I think it'd be less useful. I think you could just do SICP on its own in Lisp, because it is a dynamically typed language that it works with, and SICP wouldn't talk about like category 3 monad type stuff that you do in type functional. Learning Haskell would probably be better for porting to Scala. Someone did a JS edition based on Creative Commons license of the original scheme. Oh, that's cool. Yeah, but with these types, I think you want like you want a project that's specifically about typed functional programming. So we have that working. Add, multiply, mod, store into A the remainder. I think we'll just do the same trick. So def percent num dot from short as short mod. Yeah. And I don't know, there's no div. And right, we need a from short. So that will go into companion object of num. So def from short. This is just going to be a new num where the low is, well, we need the short. That's short. And at some point, like maybe implicit conversions, maybe, we'll see. So low bits equals s, mask it with 0xff, and then the high bits is going to be s and mask it with 0xff. Oh. Okay. Oh, right. And then we had to do 2 byte. As short mod. Oh, I guess we could do that as an int. Because we're gonna do right. This stuff defaults to int, so we should do this in int land. Okay, so we're gonna do like a from int. Which Zelda game was that from that we were just, you know, check that. We were just listening to Yeah, it's just general. Take this signed int. Hmm. Yeah, I'll definitely want to double check this later and make sure I'm not writing bugs. But I don't want to run the tests on stream. No. Yeah, I'll figure it off stream and then bring what I find here as I'm fixing things. Okay, so from int, we'll just take n and then convert things back to bytes. So if we do this in int land as int, so def as int is just going to be int. We can just do as short to int, I suppose. Yeah. So as int and n dot as int. I should maybe call that toInt. I might rename them. It's more common to have toInt. And this is all going to be from int. Oh, what were you saying about why would anyone corrupt the one true SICP with JavaScript? mm. I know Sergey Wazinski. But what is that project? Yeah, Sergey was a regular at Scala meetups. So in San Francisco, I used to host unmeetups with a Scala meetup group, which was like at a normal meetup, like you sit and you watch someone give a talk about programming. So like you're not really like meeting people and programming. It's a programming meetup. So I did unmeetups where like we got into groups and worked on like little side projects. And Sergey was always there with side projects. So I thought that was very cool. But let me pull that up. Yeah, he's a friendly guy, very smart. Oh, SOFP. The Science of Functional Programming. Oh, cool. Okay, I mean, knowing the guy, it's probably good content. I will take a look at that. Thank you for telling me about it. Yeah, thanks. I'm glad you like the meetup idea. It's the whole reason I became a meetup organizer. Um, I just wanted to have, I just wanted to write code with other people. I don't. When the pandemic hit in 2020, I'd moved to New York and I was a New York organizer. Uh, and we were doing a conference in March of 2020 in New York City. And we had to like convert the whole thing, make it virtual. And that burned me out. And the the New York Scala meetup is still dead. I haven't found another organizer. Oh, Sacramento. Okay, I have people there. That's a good place. Yeah, I know. If anyone's in New York and wants to take over the Scala meetup, talk to. I'm already talking to some people, but the discussion has slowed down. But I do want to like pass it on and get it revived. But I just don't even live in New York anymore. So it remains dormant. I think there are other meetups that fill the gap for now. But yeah, that's still a thorn in my side. I feel bad that it died on my watch and hasn't been revived yet. Okay, so we have our ferment, which means we can just implement all of these things now. We have mult, we have mod, we have add. Great, we have and or excuse me. We have and or, and we can do not. We can just do it as a method, def not and num. We can figure out the syntax later if you want to do something fancy. How would you? So this is unsigned, so it's just a full inverse. Okay. And the unary not operator is always going to be the inverse, like even in signed, right? So if we took like 1.2 binary string, we make that bigger. And if you did that with -1, that was unnecessary. Right, because -1 is just like all ones or whatever. Cool. I think unsigned signed should work the same. So from int, and we're just gonna do n.to int, or no. We're gonna do as int, and we're gonna negate that. Num.from int. Cool. Now we can implement a few more of these. So let's do mult. So this dot store in A, B times C. We can do mod. So we're storing in A, B mod C. And it's going to be same thing. Store in A, B, and C, bitwise and not store in A, not B. Okay, cool. That's all our mathy type of operators. I'm going to ignore the stack for now, but registers, let's ignore registers for now too. Actually set. How does, are these just going to be like register values? So these are going to be nums that refer to registers? So that's an error if they are not actually registers then, I guess. I'm not sure. So registers are just special memory values. That's all. Okay. And when we have a function like this, we interpret that num as a register rather than a memory location. Then maybe we have some like assert calls to make sure ranges are correct. But yeah, let's ignore registers and push and pop for now. Let's look at the jump stuff. That will help us. Well, equal and greater than, and then we'll do the jump stuff. That'll be a little bit more straightforward. SF Scala meetup isn't that active either. Oh, that's too bad. Yeah, COVID did kill a lot of groups. I know Boston and Philly died too, and I haven't kept up. But that's kind of the cool thing about Twitch is you don't need to have a meetup; you can just do it whenever. But you know, the in-person stuff is fun. B. Oh wait, not. Where did we implement not? Not doesn't need a parameter, so we can just do b dot not. Okay, so b dot not. There we go. Okay, let's do equality and greater than. So this is going to be similar to what we're doing down below. We're going to do set A to 1 if B is equal to C. Otherwise, set it to 0. Okay. So I suppose these will start with if B is equal to C. Oh, we don't need a parent. If B is equal to C, then we set A. And when we say set A, we mean write to A's memory, where I guess A could be, it's not store, is it store? So store A. I guess store then is working on registers or memory. So store at A 1. Um, from 1. I should just do a like toNum method on ints. Otherwise, 0. Else store at A num.from 0. Okay. And then we're going to take that whole thing then. Oh, wait. Our parents are messed up. Yeah, so we do that store, otherwise we do that. And I guess this whole state, the whole state that we're returning, we could then do that no output. Okay, we can clean that up in a bit. That's the general idea. If B is equal to C and B is less than or equal to C. We'll have to define our own less than. Oh wait, no, this is greater than. B is greater than C. Because the default definition for greater than is going to check. Oh, I don't think there's going to be a default definition, rather. Okay, so in Scala, I can show you this. In Scala, you can do a type class for like integral types and numeric types. So an integral type is any type that behaves sort of like an int. And what this gives you is if you say that a type is integral and like give it the minimum qualifications, then you can get all these operations for free. So all of these can be defined. All the syntax can be defined based on that. So I might do that eventually and show you how like type classes work. And then it also gives you like ordering ops and stuff like that. But for now, we're just going to define a method. So a lot of stuff that you get for free just by saying that your type is integral and like giving it the basic implementation of an integral type. Yeah, it is pretty handy. For any like numeric type, like I made my own fraction type, and then that gave me, a lot of stuff for free. So like a list, if you're sorting a list, as long as if you're an integral type, then it knows how to sort that, right? So a list of fractions, say it's integral, then you can call list.sorted, and it'll be able to sort your fractions. So that is a to-do later. To-do integral type class. And I'm going to show you another neat trick. So this is an extension method. So extension def So this is an extension on ints. And this allows us to add methods to some type like an int. And this used to be done with implicits. But now they made it part of the language. So we can do def. What are we going to do that for? Oh, we'll say toNum. So toNum, and that returns a num. And we can just do num dot from n. So now we have syntax on int. So down in places like this, we can just write 1 dot toNum. That's called monkey patching in dynamic languages. And in a statically typed language like this, it's an extension method. All right. And we still need to implement greater than. So we'll just make that another one of these methods. So infix def greater than n num. Imagine if typeclasses use keyword class. I mean, in Scala 2, well, even in Scala 3, type class don't even say that they are a type class. Like in Scala 2, it's just like a type class is a pattern that you did with implicits. Okay, so oh, Hyper Game Dev. Sorry, I missed your method. So you rated us on YouTube and you just wanted to say hi. Great. Well, thank you. Thank you for stopping by. So just so you know what's going on here, everyone who's new, we finished Advent of Code and we're doing Synacor. So this is a if you're familiar with 2019, the Intcode problems where you have like a VM, um, that's kind of the same kind of thing. It's also created by Eric Wastl in 2012 before Advent of Code. Yeah, and it's just a big puzzle like that. I assume your group was doing Advent. I have not done a YouTube raid yet. I don't know how to do that. Sorcerer. Oh yeah, thank you for the props. It was a fun AOC run. Notables are me, Bad Cop. I like Bad Cop. Twilight World, Black Silver. I don't know so many of these. Liquid Quake, I know. I like Liquid Cake. And yeah, I don't know these people. Okay, so what's wrong with this? Illegal start. Oh wait, right. We still have to define this. So we're gonna do as int greater than n dot as int, and then we'll just do num dot from int there. Oops. And oh wait. This doesn't return a num. This returns this is a boolean. Alrighty. So we use that down here. Cool. I'm just going to refactor these a little bit. Let's see. Let's do the value separately and the store step separately. So let's do this in a new line. Val result, we'll just say val x equals if then 1 dot toNum else 0 dot toNum. And then we're just going to store inside of A, it's just going to be the x value here. And then dot no output. Okay, that's much better. Twilight World did OCaml as a learning language and still builds it all out. Oh, very cool. I'm low key about it. Definitely going to keep an eye out for other languages she gets into. Okay, cool. I will add her to my follow list. OCaml's been on my list for a while. Who is it that does Ice Cold Witch? You do some OCaml, right? Okay, let's see. Do we have value from is not a member? Oh, I think it was from it. Okay, now everything should compile, right? And we still haven't tested everything. So this might be like as far as we get, is just like writing some of this out. And then next time we get to like test stuff and play around with it. And then eventually we'll run this thing on the output. But we want to make sure it's working properly before we do that, or run it on the binary. Black Silver does Zig, and Nicuevo does Haskell. Cool. You mainly do Haskell, but you don't stream. Fair. Sorcerer knows all the functional programming streamers. Great. What do we have left? We never did out. So this is code 19. This is supposed to be one of the first ones that we implement. So let's do that. Write the character represented by ASCII code A to the terminal. Right. We went on a big old detour there. So we have our no out method. Where was that? So let's define an output method. So we're going to output some value. So there's the num, and we're going to take that num and interpret as a car. So nnum, we do n.as car. Cool. Now in our out, we can just do this. Instead of no output, we do dot output a. It's silver. Sorry, what's silver? Sliver. Ah, black sliver. Oh, thank you. Yeah, I'm enjoying it too. And I know you had fun with it, so I'll be excited to like share thoughts when we get to the point where you can like share them without spoilers. Fair enough. Yeah. I mean, when she does it in Bash, like it seems she makes it look easy, right? But still, like it does sound insane to do it in Bash. Okay. So we got out. We have greater than, we have equal to, and then now we can do jump now that we have greater than equal to, or we can do jump true and jump false, I suppose. So jump, how does that work? I guess instead of progressing, jump to A. So I guess it's this dot copy, and PC becomes A, and then no output. Okay. Bash pipes are functional, totally. Yeah, she can't do an easy mode, has to make it interesting enough. Okay, jump true. If A is non-zero, jump to B. Okay, so how do we do this? Otherwise, we just progress. Oh, hold up, hold up. I just realized this no output progresses, doesn't it? No. Oh, we are forgetting to progress. So we're not using progress anywhere. Okay. So on all of these, after we store, we progress, and then we have no output. And we pass along the opcode that we use. Great. So when we jump, there's no progress. Cool. And when we output, there should still be a progress. You know, I'm not sure where. I think our output should just do the progression because we can't really progress after that. We'll think about that in a sec to do progress. Hi, Mistral. We are working on Synacor, a challenge created by Eric Wastl, who made Opcode. So since Opcode ended in 12 days this year, this is our day 13. And right now we're building a VM to interpret the binary that is the Synacor challenge. So jump true. You look at A and then jump to B. So if, well, let's see. I guess we need the next location. No, we don't even need to store next location. So if A is equal to 0, dot toNum, then we jump to B. Then this dot copy B, PC equals B, and then dot no output, right? Otherwise, we do this dot progress given our opcode, dot no output. Okay. So let's put that in separate lines here. Now jump false means if A equals 0. Jump true means not equal to 0. You are learning Java. All right. So we're doing Scala here, which has some similarity to Java. I mean, it is a JVM language for the most part. So I'm using JVM tools. Nice. How much more of this do we want to do right now? Read mem and write to read at B, write to A. Write B into A. Wait. what's the difference between these two? Read B, write to A, write B so read A, write B. It's just the same thing, but in opposite directions. So I guess for both of them, we do store, right? So for read mem, we do this dot store. So in A, we're storing the value at B. And then we progress dot new output. And then this one here is just the opposite, just to make sure I'm reading this right. So for write mem, write the value from B or write into B. So write the value from B into the memory address at A. Okay, A is the memory address, B is the value. So stores for read is actually backwards. BA. Right, the value is A. The position is B. Okay. It seems kind of unnecessary, but I assume that maybe this is assumed to be a register. So let's do a little to-do check here. To-do register check. Should that always be a register? Call. Call requires a stack, so we'll skip that for now. Return requires a stack. We'll skip that for now. And then set push pop, also stack methods. Okay. Well, I think we have a decent start. Oh, this is OP. And I might end it, wrap it up here. So quick review. We have our opcodes. There are various types. They work with a stack, they work with memory, they work with registers, and then they do math. And then there's like the jump methods. All of these have some number of parameters. And then we have a numeric type, which is little endian. So low byte first and then the high byte. And this thing here, this num type, I probably want to make this more robust, but that I will think about off stream. So we have our registers, which we aren't really using yet. We have not implemented that. But they are basically just 8 reserved memory locations. So we have a state machine, the program counter moves, so we have these helpers. And we have an optional output. And then A, B, and C refer to the next arguments, right? So we just take our program counter, we increment, and the next bit of the next couple of bytes of memory are the values that we're working with these opcodes. We still haven't figured out how to like parse the opcodes, but we'll get there next time. But we can at least interact with memory. So everything that interacts with memory, we've been implementing here, right? So we have all the math methods on the nums, and we're storing those values in our memory, which for now is just a map. But in the future, we might make that better. And yeah, I think that is a decent start. Good, I'm glad that feels familiar. And this still feels Advent of Code themed, so let's find someone to raid who's doing Advent of Code. There should still be people, right? Yeah, the interop was decent. I'll say this about Java interop. Scala has kind of abandoned being like It works. It's not as nice as Kotlin, right? So Kotlin is built to interop with Java and be a Java replacement and like live in the same code base as Java. And Scala has kind of abandoned the idea. They want to do their own thing. So it can interop, but it's not really made for interop. Alan Fan Todd's is on again. Um, he's a few days back, so maybe we rate him. And I want to see who else is doing Opcodes because we just rated him last night, right? If anyone knows who else is doing something, like I saw Bad Cop doing 2015 problems from last night. Okay, well it's just us and Howling Fan Todd's. So let's cheer him on and help him get to the finish line. And yeah, I appreciate y'all coming by and looking at Synacor here. It's we haven't gotten to the meat of it yet, but I'm excited to see like what we end up seeing as we look into this bytecode. Yes, I will check out Famistral for sure. Um, and I'll go back through the messages and look at everyone you mentioned. I'm glad you're excited. I'm excited too. And thank you. It's your fault that I'm doing this in the first place. So I appreciate the recommendation. Alrighty. I'm sending it a raid. Have a good night. Oh yeah, totally, totally.